Hello, I'm Lauren Port. I'm a graduate student in crop science at Washington State University. I'm primarily advised by Dr. Frank Young, USDA ARS, and we're working at the Ralston Project, where we are pushing no-till to its limits by growing tall cereal crops and harvesting them with a stripper header to alter the microclimate at the soil surface and conserve soil water. We're going to do a little history trip first. The Ralston Project was initiated in 1995 at the request of area growers. The region that we're talking about is the low rainfall zone, where they receive less than 12 inches of annual precipitation. And the farmers were struggling with erosion, and in this area, wind erosion can be very extreme. And so the researchers wanted to examine different crop rotations to reduce the number of years that land was spending in fallow. Phase one of the project ran from 1995 to 2000, and it was aimed at developing an economically sound and agronomically feasible system where they could grow spring crops instead of having a winter wheat tilled fallow rotation. Phase two of the research looked at using different crops in rotation, broadleaves or other cereals. And then we're currently in phase three. The results from phases 1 and 2 led to the conclusion that annual spring cropping in the low rainfall zone was not economically feasible, and so you couldn't get rid of fallow. So what we're doing now at Ralston is working to find the best way to fallow. And for us, that means a very high residue system, and that's managed through chemical fallow. So our main research questions right now are, what are the impacts of tall cereal varieties on crop residues, soil moisture, and soil organic carbon? And that soil organic carbon is a key component of the REACH project, as we're looking at how much carbon our soil can store. And then the other objective is to determine if it's possible to seed directly into the tall standing stubble that results from our crop variety and harvest choices. And then how is establishment influenced by those residues? The stripper header is really cool. Compared to your conventional cutter bar header, where there's just a blade on the front that cuts the stem of the wheat plant, the stripper header has 8 rows of mounted fingers. These fingers are mounted on a rotating drum. That drum rotates and spins and tears through your wheat with a lot of speed, but also very gently. Those fingers actually just pull the kernels from the stem of the plant, and they leave behind these really cool, basically just the cob of the wheat plant, even though we're not talking about corn. I enjoy looking at this a lot, and you're actually left with a crop or a residue that's basically the full height of the crop that was there. And we have some pictures of that. Dennis Rowe that works with us, he's standing in this field and the residue comes up practically to his waist. So that's really exciting to see. It can be really funny because it's hard to tell if your field has been harvested or not if you're driving by quickly from the road. So we have 4 treatments at this site. We're growing 2 cereal crops in the system, a winter triticale and a tall variety of winter wheat. And we chose them because they each produce a lot of residue, and we like that residue in this system, and then we make further management decisions to maintain that residue in site or on site for this fallow season. Half of our triticale plots are harvested with that stripper header that just leaves a very tall residue standing, and half of them are harvested with a conventional cutter bar header that leaves you with shorter stubble. And both of those triticale plots are managed with chem fallow. For the winter wheat, we use a stripper header on half of the plots, and then we use a stripper header, or a cutter bar header, on the other half of the plots. And those winter wheat cutter bar plots are put into a reduced tillage fallow. So we have chem fallow for 3 treatments and reduced tillage fallow for 1. I've told you we're trying to harness the straw production or biomass residue production of winter wheat and winter triticale. And compared to semi-dwarf winter wheat that was grown at the Ralston Project in phase 1 from 1996 to 2000, the winter wheat we're growing now produces a lot more residue, and we're able to leave that all standing in the field with the use of the stripper header. So a lot of the data that I'm going to talk about is comparing 2 main treatments, the winter wheat that was cut with a cutter bar and has been put into a reduced tillage fallow, and then the winter triticale that was harvested with a stripper header. So we're looking at our 2 extremes, one where there's no standing residue, and then one where there's the tallest standing residue. 3 general benefits of increased standing residue that we are measuring are temperature moderation, wind speed suppression, and possibly reduced weed growth. Here I have a graph of average daily soil temperature for a couple of the treatments. That red bar is the cutter bar triticale. So this is soil temperature just in the seed zone that we're looking at. And the blue bar is stripper-headed triticale residue, those soil temperatures. And you can see that early in the season, when temperatures aren't very extreme, there isn't much variation between these two treatments. But as we get later into the season and daily temperatures are warmer, there is more of a difference. And that difference can lead to differences in evaporation, and if we have lower temperatures, we should be able to hold more moisture in the soil. Now, the other data that I'm really excited about is wind speeds. And for the summer of 2014, we got some really great new instrumentation. Typically what you see measuring wind speeds is a cup anemometer like this one, and they'll be found on weather stations. They're often mounted a meter or two or more above the ground, and the wind hits these cups and causes them to move, and that is how the wind speed is registered. But each of these has a start threshold. There's a certain amount of friction you have to overcome to move it, and that equates to about 0.45 meters per second in this case. Rather than using the cup anemometer, because we're looking at such low wind speeds, we have a sonic anemometer, and this has no start threshold. There are no moving parts measuring wind speed. It's just a sonic pulse, and the offset of this pulse is how they calculate wind speed. It's really neat. And with this technology, we've actually been able to put these anemometers at just 6 inches from the soil surface and measure wind speed throughout the day. So 6 inches from the soil surface, if we're talking about our reduced tillage fallow, is measuring wind speeds above bare soil. But 6 inches above the soil surface in a stripper-headed triticale is this anemometer sitting there surrounded by a forest of standing crop residues. And so as you might expect, we get differences in wind speed. So this graph here shows wind speeds measured for a span of about 9 days on a stripper-headed chem fallow plot, and that's the yellow bar. And that's compared to the cutter bar tilled fallow post-winter wheat, which is the green line there. And you see our tilled fallow plot reaches a peak of about 5 meters per second, which is about 12 miles an hour, 11, 12 miles an hour, while the yellow line stays almost always below 1 meter per second. And it doesn't have very much variation to it. It's quite smooth. This data is really cool because we can all relate to it, I think. When I talk with growers, it's easy to understand that wind speeds make evaporation change, and we've all experienced that standing in front of a fan and things like that. So I really like this data set, and if you look at evaporation calculations, they frequently account for wind speed. So the other possible result from the stripper header stubble is a reduction in the weed population. And this is something we haven't directly tried to quantify, but we've made observations about it, and we've had some growers make observations about it as well. So we noticed that in our cutter bar harvested plots, we had more weeds than in the stripper header harvested plots. And in our tilled fallow, we had even more weeds. And I can tell you because I was responsible for pulling some of them this year. But one of the reasons that we see this difference, we think, is due to just the amount of light that reaches the soil surface. So if you don't get light down to the soil, those seeds aren't going to germinate, or they aren't going to grow very strongly. And the really great thing is that we shared this observation with some farmers, and one of them, who uses a stripper header in his operation, said, you know, we've been using a stripper header for a good long while now, and this fall we decided to forego one of our Roundup applications because the weed population just wasn't there. And I think that's a really exciting result. He ended with a caveat that we can't say how that'll go until the springtime to see if that was a mistake or not, but it's something. It's definitely something. So we've summed it up. We talked about soil temperatures, wind speeds above the soil surface, and lower weed population that we have observed. And all of these things together can lead to more soil water. The low rainfall zone receives most of its rainfall during the wintertime. The soil then stores that, and we want to capture that stored soil moisture for the planting of the crop. And so if we can reduce evaporation by reducing temperatures and wind speeds, we can have more soil moisture, as we saw in 2013 and 2014 when we planted winter canola. So the data that we show here is for the top 3 inches of the soil. And we're interested in that zone because we're trying to diversify the rotation with the inclusion of winter canola. And winter canola is small seeded. You can't plant it more than 3 inches deep. So we're interested in this maybe shallower zone than a wheat grower would be. But what you see in the graphs for both years is that at planting time, our stripper-headed triticale fallow had more moisture in it than the reduced tillage fallow. And that was instrumental in getting a really good stand of canola in 2013. In 2014, everything was so dry. There's not a profound difference between dryness levels, and our stand wasn't quite so great. One difference we did see in 2014, though, we were digging around in the seed zone to look for these canola seedlings after we'd planted. We wanted to know what was happening, if they were germinating at all, if they were getting burnt off before they could emerge. And what we noticed was that in the stripper-headed plots, the soil temperatures in that seed zone were cooler. You could feel it with your hands, how much cooler the soil was in that area than when you were digging through the seed zone in the tilled fallow. So we put some temperature probes out there. This is September 17th through 27th, so it's actually 3 weeks or a month after planting. But you can see there are quite noticeable differences in soil temperatures. And for canola, this can mean a lot. It can keep the seedlings from being burned off. It'll reduce the amount of water that they transpire during the daytime. It can have a pretty significant effect, and we're really excited to see these values. So in 2014, as I alluded to, we didn't have the best establishment because there was kind of no water anywhere. We were working with very little, but we did get some establishment, and what we found is that in our chem fallow plots, with a stripper header especially, we get better establishment than in the reduced tillage fallow. So, in summary, we're building residues in an undisturbed system. That's great, and that could have implications for soil carbon. And we were able to successfully seed directly into standing stubble in this high residue system, which farmers are really interested in. A lot of people, they look at the residue loads we're carrying, and they wonder if they can pull a drill through that, and if they can even seed into it. So we've shown that you can. So now I've looked at the data that has been collected up until this point. So where do we go from here? Well, I'm going to do some studies in the lab. First, trying to measure the actual permanent wilting point of this soil at Ralston, and that'll help us determine just how dry things were in 2014. And in conjunction with that, we'll do a germination test to look at how much water is required for germination of this winter canola. And that should tell us a little more about the differences in water content and how they affect germination and establishment. We'll also be doing another year of gravimetric water content sampling on the plots to see if there's a difference in that evaporation or loss of soil moisture due to this increased residue load. And then either in the spring or fall, we're going to be taking another set of soil samples that we'll analyze for soil carbon and soil nitrogen. And we will compare these to samples that we took in the beginning of the project to see if the carbon and nitrogen has increased, and if we can say that this system is acting as more of a sink for atmospheric gases than a more conventional system does. That's it. Thank you.